But of course, computers are not all math. And in fact, we'll use very little math per se in this class. And so let's move away pretty quickly from just zeros and ones and talk about letters of the alphabet, say in English. Here is the letter A. Suppose you want to use this letter in an email, a text message, or any other program. What is the computer doing underneath the hood? How can the computer store a capital letter A in English if at the end of the day, all the computer has access to is a source of electricity from the wall or from a battery, and it has a lot of switches that it can turn on and off and treat the electricity in units of 8 or 32 or 64 or whatever? How might a computer represent a letter A? Yeah, we need to give it an identity, so to speak, as an integer. In other words, at the end of the day, if your entire canvas, so to speak, consists only of zeros and ones, like that is going to be the answer to every question today. You only have zeros and ones as the solution to these problems. We just need to agree what pattern of zeros and ones, and therefore what integer, what number, shall be used to represent the letter A. And hopefully, when we look at that pattern of zeros and ones in the right context, we'll indeed see it as an A. So if we look inside of a computer, so to speak, in the context of like a text messaging program or a word processor or anything like that, that pattern shall be interpreted, hopefully, as a capital letter A. But if I open up Mac OS's or Windows or my phone's calculator program, I would want that same pattern of zeros and ones to be interpreted instead as a number. If I open up Photoshop, as we'll soon see, I want that same pattern of zeros and ones to be interpreted as a color, presumably, not to mention videos and sound and so forth, but it's all just zeros and ones. And so even though I, when writing that chat program a few minutes ago, didn't have to worry about telling the computer, oh, this is text, this is a number, this is something else, we'll see as we write code ourselves that you as the programmer will have control over telling the computer how to treat some pattern of zeros and ones, telling it this is a number, this is a color, this is a letter, or something else. How do we represent the letter A? Well, turns out a bunch of humans in a room years ago decided, this pattern of zeros and ones shall be known globally as a capital letter English A. What is that number if you do the quick mental math? So indeed, 65, because we had a 1 in the 64's place and a 1 in the 1's place. So 65, that's just sort of it. It would have been nice if it were just the number 1 or maybe the number 0. But at least after the capital letter A, they kept things consistent, such that if you want to represent a letter B, it's going to be 66. Capital letter C, it's going to be 67. Why? Because the humans in this room, a bunch of Americans at the time, standardized on what's called ASCII, the American Standard Code for Information Interchange. Doesn't matter what the acronym represents, but it was just a mapping. Someone on a piece of paper essentially started writing down letters of the alphabet and corresponding numbers so that computers subsequently could all speak that same standard representation. And here's an excerpt thereof. In this case, we're seeing 7 bits worth, but eventually we ended up using 8 bits in total to represent letters. And some of these are fairly cryptic, maybe more on those another time. But down here, if we highlight just one column, we'll see that indeed, on this cheat sheet, 65 is capital A, 66 is B, 67 is C, and so forth. So why don't we do a little exercise here? What pattern of zeros and ones do I see here? I've got 3 bytes, so 3 sets of 8 bits. And even though there's no placeholders now over the columns, what is this number? It's 60. Yeah, so we got the 1s, 2s, 4s, 8s, 16, 32, 64's column. So indeed, this is going to be the number 72. 72. This is not what computer scientists spend their day doing. This is just to reinforce what it is we just looked at. And I'll spoil it. The rest of these numbers are 72, 73, 33. And anyone in this room could have done that if you took out a piece of paper, figured out what the columns are, and just do a bit of quick or mental or written math. But this is to say, suppose that you just got a text message or an email that if you had the ability to look underneath the hood of the computer and see what pattern of zeros and ones did you just receive over the internet, suppose that pattern of zeros and ones was 3 bytes of bits, which, when you do the math, are the numbers 72, 73, 33. Well, here's the cheat sheet again. What message did you just get? Yeah, so it's high. Why? Because 72 is H and 73 is I. Now, some of you said hi fairly emphatically. Why? Well, 33, turns out, and you wouldn't know this unless you looked it up or someone told you, is an exclamation point. So literally, if you were to text someone like right now, if you haven't already, HI exclamation point in all caps, you would essentially be sending 3 bytes of information somehow over the internet to that recipient. And because their phone similarly understands ASCII, because it was programmed years ago to do so, it knows to show you HI exclamation point and not a number, 3 numbers no less, or colors, or something else altogether. So here we then have hi. 3 digits in a row here. What else is worth noting here? Well, there's some fun sort of trivia embedded even in this cheat sheet. So here again is A, B, C, D, E, F, G, and so forth, 65 on down. Let me just highlight over here the lowercase letters, 97, 98, 99, and so forth. If I go back and forth, does anyone notice the consistent pattern between these two? Yeah, so the lowercase letters are 32 away from the uppercase letters. Well, how do we know that? Well, 97 minus 65 is, 32. 98 minus 66 is, OK, 32. And that pattern continues. What does this mean? Well, computers know how to do this. Most normal humans don't need this information. But what it means is if you are representing in binary with your transistors on and off representing some pattern, and this is the pattern representing capital letter A, which is why we have a 1 in the 64's place and a 1 in the 1's place, how does a computer go about lowercasing this same letter? Yeah. Perfect. All the computer has to do is change this 1 bit in the 32's place to a 1, because that has the effect mathematically, per our discussion, of adding the number 32 to whatever it is. So it turns out you can force text from uppercase to lowercase or back by just changing a single bit inside of that pattern of 8 bits in total. All right, why don't we maybe reinforce this with another quick exercise? We have an opportunity perhaps here for maybe to give you some stress balls right at the very start.